Alright, in this lesson we're going to continue evaluating definite integrals, but we're going to do some where maybe we need to change the original function. Maybe it's more complicated. So a couple of lessons ago we used something called substitution, where we chose the most complicated part of the function and we substituted in u for that. So we're going to do a similar process today with definite integrals, because remember when we did that a couple lessons ago, that was with indefinite integrals. Okay. So you might want to refer to the video for that if you were a little shaky on that, but you're going to use the same steps as before. In other words, I don't want to list them all out. You're going to decide what your u is based on the most complicated piece, find the derivative of that, okay, and make an adjustment if you want. The only difference here is you're gonna also change your upper and your lower limits to be in terms of u. So remember, before we didn't have upper and lower limits when we did substitution, so that really wasn't a thing, but now we do. So we're going to change everything to be in terms of u. And then the great part about this is once you do that with these definite integrals, you will not need to go back and plug in the original like we did before. So you will not need to plug in anything for u at the end, because frankly there won't be any u terms left at the end. We'll just be left with a number. So I hope you'll watch this video and actually pay attention to the process, because there are a couple spots you can kind of get messed up if you don't pay attention. But certainly go back and rewatch the video for 13.2 if you were a little shaky on this topic. But let's find the antiderivative from 0 to 2 of x times x squared minus 1 to the third power dx. So just like before, we're going to try to write this in a simpler fashion. So we're going to let u be the inside piece, which in this case is x squared minus 1. Notice that du is 2x, and then don't forget we end in this notation. Okay, so this is just notation. We did this before. So notice we are going to need to make an adjustment. So let's talk about what I have. Here I have u cubed, right? But here I don't quite have what I want, right? I have x, and what I'd really like to have is 2x, okay? Or, in other words, I want to change this in some way. So notice that I wanted x dx, because that's what I have over here. I have x dx. Okay, so what constant would make that adjustment for me? Notice if I did 1/2 du, that would cover it. Okay, in this example, notice that the x dx's are kind of separated from each other. If you wanted to, you could put those together. So notice if I did 1/2 times 2, I would get 1, just like I want. But here is how these differ. Okay, so I'm also going to want to change the upper and the lower limits. So the upper limit currently is x equals 2. So all you're going to do is plug that into the u equation to write that upper limit in terms of u. So we get 3 here. And then we're going to find the lower limit, which currently is 0, x equals 0. But if we write this in terms of u, it would be 0 squared minus 1 or negative 1. Okay. So now when you go to do the rewrite step, this is the most important piece. Now we're going to be doing the integral from negative 1 to 3. We change that upper and lower limit. Okay. And then write what we have here. We have 1/2 u cubed du. Okay, so if you need to pause the video to figure out how we got there, then do that. But we made the complicated part u, right? We simplified that to be u cubed, and this adjustment is because I wanted this to be x, not dx. Okay, and then I changed the upper and the lower limits. And now I'm just going to perform my antiderivative as normal. Constant gets pulled down, right? What is the power that we're going to bump this up to? We're going to bump it up to 4, so it'll be 1/4 u to the 4th. Okay, and then remember this notation means, hey, I'm going to plug in 1. Oh, sorry, I'm going to plug in 3, and I'm going to plug in negative 1, and I'm going to subtract them. So in the end, this is what I really have. I have 1/8 u to the fourth, and I need to plug in -1 and 3. So I need to find f of 3 minus f of -3, or -1. So let's do that. So here is my f of 3, and here is my f of -1. So I end up getting 1/8 times 3 to the fourth. Notice I'm just plugging it in this equation, and this would be 1/8 times -1 to the fourth. So if you work all of this out on the calculator, you're going to get 10.125 minus 0.125 if you do it in stages. In other words, you get 10. Okay. So interestingly enough, I'm only going to show you this with really one example. You can actually check both the original function and the u function, and you will actually get the same area, although the functions will look very different. So let's do our trick where we check in the calculator. So let's go with the original. X times x squared minus 1 raised to the third power. Remember what that looks like. We go second trace, and then we choose the one that looks like an integral symbol, which for my calculator is choice 7. So you have to give it a minute to graph. Okay, mine took a little minute there. And then you tell it, I want the integral. It's asking me for lower limit, so I'm going to say 0. And then it's asking me for upper limit, so I'm going to say 2. And then notice it gives me an answer of 10. I know that's a little hard to see, but here is where it's giving this to me. You'll need to practice this on your own calculator. Okay, so notice that's the answer I should get there. But interestingly enough, it also works if I go back to this step. And in other words, if I use the u step, even though the function's way different. So let's clear out everything I have there. So 1/2 times x cubed. Now I'm doing this equation, and notice there is no u, so I have to use x. Okay, and if I do the same thing, but notice my limits have changed, right? I'm doing this check step for now. Okay, so if you plug this in and you go from the lower limit of -1 to 3, notice it still colors it in, and I know it's hard to tell, but it still tells me the answer is 10. Okay, so you can check either one of these equations on your calculator, and you should get it to tell you that the answer is 10. Okay, now you don't have to check it on your calculator. That's just one way for you to kind of know and have confidence that, hey, I did that right. All right, let's look at another problem where maybe we need to make an adjustment. So the integral from 0 to 1 of x times 5x squared plus 4 dx. So we didn't do this on the last one. Maybe we should do this on this one. Let's rewrite this. This would be the inside portion to the 1/2 power, and then times x dx. In other words, let's go ahead and simplify out and rewrite that in exponential form and see if that helps us. So I'm going to let u be 5x squared plus 4. That's the inside piece, right? So notice the derivative of that would be 10x, and then don't forget your notation of dx. Okay, I'm underlining this because that should always be there. It's just notation. But notice if I go back over here, I can rewrite this as u to the 1/2, but I struggle when I get here, right? So notice that I want this to look like x dx. In other words, I do not want that 10 there. Okay, so how can I get rid of a 10 by multiplying by a constant when I want it to not be there? I can just do 1/10 du. Okay, so, and then don't forget that you need to change the upper and the lower limits as well. So the current upper limit is 1. So if you plug that into your u equation, you'll get 5 times 1 squared plus 4, or 9. And the current lower limit is 0. So if you plug that in, you get 5 times 0 squared plus 4, or 4. So the most important part is that you can get to this stage. My new equation that will be simpler to find the antiderivative of is the antiderivative, or the integral from 4 to 9 of, now let's write what I have here, 1/10 u to the 1/2 du. Okay, that's a lot simpler than what we had here. So we'll pull the constant down, right? Be careful with fractional exponents, right? So notice that we need to add 1 to the power, right? So it's 3/2 if we add 1 to it. So it's 1 over 3/2 and then u to the 3/2. And then we'll evaluate that eventually from 4 to 9. But let's go ahead and clean that up. Okay, so if we use a calculator, I would clean that up with a calculator. This is really just going to be 1 over 15 u to the 3/2, and we're still going to take it from 9 to 4. So we need to do one minus the other, right? So plug in the first one, 1 over 15 times 9 to the 3/2, and then this one would be 1 over 15 times 4 to the 3/2. Okay, those are exponents. So if you work that out on your calculator, you're going to get 19 over 15. Okay. Notice if you check this one on the calculator, you know, you will only get a decimal version, right? So I mean, what I mean by checking it on the calculator is if you use the graphing portion of the calculator. So be careful that you don't rely too heavily on that. Okay, that's kind of important. Okay, so let's look at a few more. So the integral from 0 to 1 of 1 over the square root of 2x plus 1 dx. Okay, so the first thing is, let's rewrite this as 2x plus 1 to the negative 1/2. Okay, it's 1/2 because of the square root. It's negative because it's in the denominator. So I'm going to let u be the inside piece. So the derivative of that is 2 dx. Okay, this is just notation. So let's talk about what I have. Here I have u to the negative 1/2. But here I don't quite have what I have here, right? So notice I don't even want any number there. I actually just want 1 dx. Okay, so how can I get rid of that 2? I can multiply by 1/2. So this is just 1/2 du. Okay, notice this right here is just the adjustment. We talked about this back in 13.2. Okay, what adjustment do I need to multiply this by so that I get what I want up here so that it's perfectly represented? And then last but not least, I need a new upper and lower limits. So the current upper limit is x equals 1. So if I plug that in, 2 times 1 plus 1 is 3. The current lower is 0. So if I plug that into the u equation, I'll get 1. So most important part of the whole problem, my new integral that is going to be easier to solve is the integral from 1 to 3. I got those from here, right? Now just read off what you have here. 1/2 u to the negative 1/2 du. So notice that has fractional and negative exponents, but it's still a lot simpler than what I started with there. So as usual, constants get pulled down. Okay, ask yourself, what happens if I add 1 to negative 1/2? And the answer is I get 1/2, right? So it's 1 over that new power, and then u to that new power. And then I want to evaluate that from 1 to 3. But if you work these out on the calculator, you're going to see actually that these cancel each other out. This becomes 1. So we end up just getting u to the 1/2 evaluated from 1 to 3. Okay, so let's go ahead and plug this in. We want first thing plugged in, and then subtract the second thing plugged in. Okay, so notice, something to the 1/2 power, this is just a decimal, so this would just be square root of 3 minus square root of 1. Well, square root of 1 is just itself. So this is the exact answer. This is the answer that I'm going to want. Okay, so use the exact answer when you can, but when you go to check it on the calculator, you will need to kind of know what this is. So let's just see what square root of 3 and then minus 1 is. Notice this is supposed to be like 0.73. Okay, so let's check it on the calculator and see. Okay, I always go with the original function. So it's 1 divided by square root of 2x plus 1. And then I'm going to second trace. And the 7th choice is antiderivative. The original lower limit was 0. The original upper limit was 1. And notice, again, I know it's kind of hard to see, but I've checked it, okay? This checks out on the calculator, so we're good to go. But this that I circled would actually be the answer that you would want. Notice this would not be something you could get from the calculator, okay? The calculator is going to give this to you, and you have to know the exact answer. Okay, so what about the integral from 0 to 2 of 2x e to the x squared dx? So we're going to let u equal the exponent of e. Okay, when you have an e function, more than likely, not always, but most of the time your derivative or your u should be the exponent. But the reason we want that to be is because we want to somehow talk about the derivative of that also, which is 2x, and notice that's represented as well. Okay, so let's rewrite this if it helps. This is really the derivative from antiderivative from 0 to 2 of e to the x squared power times 2x dx. Notice I don't even need an adjustment. This would be e to the u, and this is perfectly du. Okay, so here, no adjustment needed. So sometimes you're going to run into problems that need adjustments, and sometimes they don't. Okay, but you still need to change the upper and the lower limits. So the current upper limit is 2, the current lower limit is 0. So u would be 2 squared or 4. I'm just going up to the u equation and plugging that in. Here u would be 0 squared, which is still 0. So the most important thing again is, can you do the rewrite step? So it's now the integral from 0 to 4, and now just read off what we have here. E to the u du. Okay. Notice how much nicer this is than this, right? It's only one thing, and it's just e to the u power instead of e to some weird power like that has. So what's the antiderivative of e? Just itself. And then don't forget we need to plug in 4 and 0 and subtract them. So we have something minus something else, right? So it's going to be, I'm sorry, that should have been e to the u. I got ahead of myself. That's e to the u. But when we plug in 4, we will get e to the 4th minus e to the 0. Okay, but anything to the 0 power is just 1. So this would be the exact answer that I'd be looking for. But again, on your calculator, it's going to give you an answer of, let's see, I'm not going to do the whole thing, but e to the 4th minus 1. Your calculator's only going to give you 53.598, blah, blah, blah. Okay, so keep that in mind. I'm going to move the calculator away just for a minute. Now what if I asked you to find the area under the curve of f of x equals 2x e to the x squared power from x equals 0 to x equals 2, rounded to the nearest tenth. Okay, so notice this is the exact same equation we started off with in the first part of this problem, and the same limits. Okay, so the answer is going to be approximately what we got on the calculator. Okay, so I'm going to move that back. So it's going to be approximately what we had here, right? So we wouldn't list the area as e to the 4th minus 1. So we're going to round it to be 53.6 units squared. Okay, remember area is always something squared. All right. So the integral from 0 to 1 of 32 x squared plus 1 to the 7th, and then x dx. So there's a lot going on in this problem. So I would certainly suggest that you write the complicated piece first. So I'm not going to do anything other than just rewrite this. So this is times 32x dx. I want to be able to separate the u portion and the du portion, so let's see if I can do that. So I would make u x squared plus 1. So du is 2x dx for notation. So notice when I come try to write what this will be u to the 7th. But this is definitely not what I have, right? Okay. So notice I want 32x dx. Okay, so think about what adjustment I could make. What could I do to 2 that would give me 32? Okay, notice that I could multiply by 16. So 16 du is what I have here. Okay, note this right here is the adjustment so that these are going to be equal. Okay, still have my upper and lower. So the upper is x equals 1. The lower is x equals 0. So if I have u equals 1 squared plus 1, it's 2. For 0, if I plug that into the u equation, I get 0 squared plus 1, or 1. So, important part. The new integral is the integral from 1 to 2. Those were my new limits I just found. Okay, and then let's just rewrite what I had over here. 16 u to the 7th du. So let's perform this antiderivative now. Pull the 16 down, bump the power up by 1, and raise u to the new power. And then don't forget we're going to evaluate it from 1 to 2. So in other words, this is just 2 u to the 8th from 1 to 2. So in the end, we want two things being subtracted from each other, right? So this would be 2 times 2 to the 8th minus 2 times 1 to the 8th. So this is going to be quite large, right? This would be 510. So if I were going to check this on my calculator, I might even have to expand my window out a little bit, okay? Because it's just going to be a big, big area. All right, last one, and then we're going to use kind of a variation of this formula or this method to talk about something called average value. But for now, let's try to do this last problem. All right, so we did this before. Remember, it is probably a good idea to separate this into pieces when you have a fraction. In other words, write 1 over that and then times this dx. We want them in separate pieces again so that we can talk about them in terms of u. So I'm going to let u be the biggest power thing, so it's going to be this. So the derivative of this would be 3x squared plus 6x dx. Notice if there are more than one terms here, you have to put that in parentheses. So let's talk about what I have. Here I have 1 over u. Hopefully you recognize that as our special case. And here, notice this does not match up. Okay? So notice what I want, right? I want it to be x squared plus 2x dx. But what I have is 3x squared plus 6x. So let's see if we can factor something these have in common. In other words, I'm going to factor a 3 out. I know I technically could factor an x out, but I don't really want to because I want to talk about how I actually almost have what I want, right? I just have 3 times what I want instead of just the parentheses that I would like. So how do I get rid of a 3 when I don't want it there? I just multiply by 1/3. The more you do of these, the easier it will be to understand what adjustment you need. Okay, but all the watching me do it in the world is not going to be a substitute for you practicing it on your own. So the current upper is x equals 2. The current lower is x equals 1. So we're going to have 2 cubed plus 3 times 2 squared minus 1. So let your calculator do that, but it comes out to be 19. Here you're going to get 1 cubed plus 3 times 1 squared minus 1, or 1. Sorry, that's not 1, that would be 3. Because it'd be 1 plus 3, which is 4, minus 1, which is 3. So this is what I have. My new integral is quite different from what I started with. It's from 3 to 19, and I have 1/3 times 1 over u du. So notice, if you can get this part right, you're just transferring over all the new stuff that you have, right? So when I have a constant, I pull the constant down. Don't forget this is the special case, right? So this would be the natural log of u, evaluated from 3 to 19. So in other words, if I want to, I could actually write the 1/3 out to the front, since I'm going to multiply it times both things. So I would get 1/3 times the natural log of 19 minus the natural log of 3. And then we had one like this before. We can combine logarithms that we are subtracting by using the quotient rule for logs. So if I want the reduced final answer, it's actually 1/3 times the natural log of 19 over 3. This would be the exact answer. Okay, the calculator is going to spit me out some sort of decimal that's equivalent to that, okay, or at least an approximation. So remember, anytime you're subtracting logs, you can combine them into 1 by dividing them. Okay, and that 1/3 stayed because the 1/3 was going to get multiplied by both things. Okay, so the last thing in this lesson is we can also discuss what the average value of a function is. In other words, maybe we had sales for a company over a 20-year span and we just want to know what the average sales are, okay? And maybe it's a complicated formula to talk about the sales from year to year, which, to be honest, most real-life scenarios are complicated equations. So the average value of a function over the interval from a to b is an application of antiderivatives. It is 1 over b minus a, and then you take the integral from a to b of that function, and then don't forget your notation dx. So anytime you see average value being talked about, you will be using this formula. Okay, so let's look at a couple examples that use that. But honestly, the math involved is going to be really close to what we've been doing. So the total cost of manufacturing X dictionaries is C of X equals 20,000 plus 10X. So for part A, I want you to find the average value of the total cost. And let's do on the interval from 0 to 1,000. So when you're given an interval, that's going to be your A and your B. So if you're being asked to find average total cost, it would just be 1 over B minus A. Okay, my A and my B are 1,000 and 0. And then it will be the integral from the same limits, 0 to 1,000, of the function that you were given, 20,000 plus 10x dx. Okay, so notice we don't need u substitution for this problem. Okay, this is just a simple integral that I can find the antiderivative of. So this is going to be 1 over 1,000. In other words, this just serves as a constant being multiplied outside. Okay, and then let's see if I can take the antiderivative of this. This would be 20,000x, right? Think about it like you're bumping the power up by x, but there isn't a power of x, right? So, or think of it like which function, when you take the derivative of it, would give you 20,000. It would be 20,000x. For this one, pull down the 10, bump the power up by 1, multiply by x to the new power. And then don't forget this notation which says, hey, I'm going to plug in 1,000 and 0 and subtract them. So let's kind of clean this up a little bit. So this is 1 over 1,000 times 20,000 x plus 5x squared. And we still want to plug in 0 and 1,000. So there's a couple of ways to write this. I'm just going to write 1 over 1,000, and then I'm going to do the first thing minus the second thing. Okay, notice that's always how we do antiderivative, right? We plug the top number in minus the bottom number being plugged in. So this would be 20,000 times 1,000. Didn't really leave myself enough room here. 5 times 1,000 squared. And this would be 20,000 times 0 plus 5 times 0 squared. Okay, well notice that's just going to be 0, right? So now we just need to figure out what this is. Okay, so use your calculator. I'm not even going to enter in the last part. So it's 1 over 1,000. I'm not going to enter in this because I know it's a big fat 0, but you can. So it's 20,000 times 1,000. Whoops, one too many zeros. Plus 5 times 1,000 squared. If you want to, go ahead and enter in the minus part there, but that's just 0. Okay, and then notice in the end you get 25,000. So 25,000 is the average total cost. Okay. Notice that's not actually the average cost per dictionary. Okay, that's the average total cost as we go from making 0 dictionaries to 1,000 dictionaries, which is quite a big swing. So for your participation grade for this week, I want you to email me the answer to example 7. Okay, so the answer to example 7 is just $25,000 in average total cost, and that's what I want you to email me. All right, so last question of this lesson. And I hope you'll look at these last two problems and really look at the differences and try to think about when do I need to use substitution versus when do I not. In example 7, I didn't need to use substitution because it was a really easy function. I only use substitution when the function looks complicated and I think I can make it look simpler. All right, so the sales in $1 million for a company. Looks like this. Where T is the years since the startup or since the company started. Okay, and I want you to find the average sales for the first 5 years. By the way, realistically, you don't judge the future of a business that just started on their first 5 years. Okay, so for lots of reasons. Sometimes they don't necessarily do all that well their first 5 years, but sometimes they actually start up really fast, and it doesn't mean they're always going to, you know, enjoy that kind of growth, so you have to be careful about that. But I asked you to find average. Okay, so, and it's average for the first 5 years, so this is what this is going to look like. 1 minus 5, or 1 over 5 minus 0, because it's from 0 to 5 years. And then it'll be the integral from 0 to 5 of t times the square root of 0.2 t squared plus 4 dt. Okay, that's just the formula for average. Now notice, compare this one to example 7. This one looks more complicated, right? So this is certainly a time where we might want to use substitution. So I'm going to let u be the complicated part, right? U is going to be 0.2 t squared plus 4. And then notice the derivative would be 0.4 t, and then don't forget the dt. So if I come back up here, this can be taken care of by saying u to the 1/2. But this t dt is not quite what I have here, right? So notice what I want is I just want plain t dt. Okay, so I have a 0.4 that I don't want there, so what adjustment could I make if I want to get rid of something? So notice I didn't really write this one the same way, but I'm just going to divide by what I don't want. Okay, I don't want the 0.4 there, so I'm just going to get rid of it. So again, although this is an odd adjustment, this is just the adjustment that I have to make so that this new equation will not be different from my original equation. And then I still need to change the upper and lower limits. So the current upper limit is 5, x equals 5. The current lower limit is x equals 0. So let's plug that in, 0.2. You'd want to have your calculator out, times 5 squared plus 4. That is going to equal 9. For the lower limit, it's 0.2 times 0 squared plus 4, or 4. Alright, so let's see if we can get this right. So the new equation is going to be 1 over 5, because that comes from here. But now we're going to be going from 4 to 9, because I changed my limits here and here. And then I've got 1 over 0.4, okay? So let's figure out what that is, because by the way, you could write it as 1 divided by 0.4, but it's easier written as 2.5, okay? So I'm just going to write this as, actually, let's just leave it as 1 over 0.4. Okay, it's not the end of the world for that to be there. And then notice I have u to the 1/2 du, just so we don't confuse what's going on here. So let's combine these. Okay, let's do 1/5 times the 1 over 0.4, and notice we're going to get 0.5. So I'm just going to clean this up, and this will be 1/2 times the integral from 4 to 9 of u to the 1/2 du. Okay, so all I did was combine this guy and this guy together to give me this. So now I need to bump the power up by 1. So it will be 3/2. So 1 over new power, u to the new power. And then we're going to evaluate from 4 to 9. So in the end, you get 1/3. And then we're going to plug in the 9 and the 4. So what do I get here? I get 1/3 times 9 to the 3/2 here. I get 1/3 times 4 to the 3/2 here. So notice I'm looking for average sales, so it would be probably appropriate to round to the nearest maybe 2 decimal places. So this comes out to be 6.33, and then don't forget, if you read the problem originally, it's million per year. Okay, so this startup company was having sales of an average of 6.33 million per year, but it could have been, you know, that certain years were better than others.